Welcome to this session. In this session, we state the Cauchy integral formula and then prove the formula. So the statement. So the Cauchy integral formula states that if a function f of z is analytic, within and on a closed curve C, and if A is any point within C, then the integral of f of z over z minus a along this curve C with respect to z is given by 2 pi I times f of a. So this is the Cauchy integral formula, that if a function f of z is analytic within and on a closed curve C, and if a is any point within C, then the integral of f of z over z minus a along C with respect to z is given by 2 pi I times f of a. Another way of rewriting the same formula is to say f of a is given by 1 over 2 pi I integral along C of f of z over z minus a dz. So these two actually means the same thing. Now let's provide the proof for this formula. Proof. So consider the function f of z divided by z minus a, which is analytic, at all points within C except at z equals to the point A. Now, within the point, or the point A, not within, so the point A at the center, and radius r units, draw a small circle, call it C1, lying fully within C. So C is our big or the largest curve. So this is what I mean. So let this one be A, and then I have this. So this is the direction. So call this one C1. So this way I have the point A. This is the curve C. So we have general point Z within this region. So that's what we have. So now f of Z over Z minus A is analytic in the region between C and C1. So hence, by Cauchy's integral theorem, for multiple connected region, we have so this integral of this analytic function f of Z over Z minus A along C will be given by the integral C1 f of Z over Z minus A dz, which will be the same as the integral along C1. And then we can write this f of Z as f of Z minus f of A, and then plus f of A divided by Z minus A dz. There's nothing I'm changing because when I simplify, I still get numerator to be f of Z, which can be written as the integral along C1 of now these first two terms I put together, f of Z minus f of A divided by Z minus A dz, plus now I have f of A integral along C1 of dz over Z minus A. So let's call this one question 1. Remember what I've done here is when you have a number A minus B plus C, divided by, say, x plus a, you can write it as a minus b over x plus a plus c over x plus a. So this is how I have split this numerator into two parts, f of z minus f of a, and then with the denominator, and then f of a, since this doesn't have a z, is just a constant, that's why I factored out the integral sign, and then dz over the denominator, z minus a. So let's call that one equation 1. Now, next, for any point on the curve C1, this is what we have. And then now, the integral on C1, f of z minus f of a over z minus a dz can be written as integral from 0 to 2 pi of f of a plus r e raised to power I theta minus f of a divided by r e raised to power I theta times I r e raised to power I theta d theta, since z minus a can be written in the form r e raised to power I theta. So where this is the exponential form of the complex number, which implies that the z is the same as ir e raised to power theta I or I theta d theta. So that's why we have this relation. So where the z you replace by a plus r e raised to power I theta. This remains to be the constant f of a. Z minus a is given by r e raised to power I theta. And then dz you replace by its equivalent value in terms of theta. So this is what we have. So this will give us integral from 0 to 2 pi, and then f of a plus r e raised to power I theta minus f of a, and then you multiply by I d theta, and this will give us 0, where r tends to 0. So when you let r approach 0, when the distance or the radius is very, very small, so this will just be f of a. So f of a minus f of a is 0. So that integral will be 0. So we can say for this other integral along C1 of dz over z minus a, we can write it as integral from 0 to 2 pi, and then I r e raised to power I theta d theta over r e raised to power I theta. So this is a value of z minus a, which will be the same as integral from 0 to 2 pi, and then I d theta. This will give us I theta from 0 to 2 pi, and this will give you 2 pi I. So now putting these values in, so this is the, we can call this one equation 2, call this one equation 3. So replacing 2 and 3 in 1, we get the integral along C of f of z dz over z minus a is the same as the first integral is 0 plus, then remember this is 2 pi I, but we had another constant f of a. So this f of a times 2 pi f of a times that 2 pi I. So i.e., this implies that 2 pi I times f of a is the same as the integral along C of f of z divided by z minus a dz. Or you can rewrite it as making f of a the subject. We say f of a is given by 1 over, so we'll divide through by 2 pi I integral along C of f of z over z minus a dz. This proves the theorem that we stated, or the formula that we gave at the start of this session. So this is the Cauchy integral formula. The next session we will state and derive the Cauchy's integral formula involving derivatives of functions. Thank you.